Containers. We're already hours into the course, and it's only now that we're finally getting into containers? Wow. Well, here we are, and here's the plan. We'll have a quick big picture, then we'll dive in, we'll touch on login, and then we'll wrap it up. Now, of course, as we go about things, we're going to touch on some of the exam stuff. From Domain 1, we'll inspect images, add networks, and publish ports. From Domain 2, we'll look at some of the Docker inspect outputs. And from Domain 4, we'll publish a port, then see how we can find out which port a container is accessible on. That's it. Let's do it. Okay, first up, in the Docker world, the most atomic unit of scheduling is the container. It's the smallest unit of work we can create. So, in the virtualization world, that's the VM. In the Kubernetes world, it's the pod. Well, with Docker, it is the container. This means if we want to roll out an app on Docker, we do it as one or more containers. Sure, there's higher level objects like services and stacks and pods if you're rocking with Kubernetes on Docker. But the smallest unit of work in the Docker world is the container. Now then, containers are running instances of images. We've got build time here, run time here. And we know that images are a bunch of layers, read-only, yeah? Well, digging a bit deeper, all a container really is a thin, writable layer lashed on top. So, build time down here, run time up here. This means any writes and changes that we make while the container's running all happen up here in the writable container layer. Now, all of this is done through the magic of union file systems or union mounts, where all of this layering and stacking here gets hidden and everything is made to look like a single unified layer. Anyway, we can have a one-to-many relationship between images and containers. So each container that we're showing up here, well, it's really just a unique and separate writable layer, remember? And each one in this example is linked back to a single read-only image down here. So, if we're running a couple of containers off of this image, and this one here wants to edit a file in the image, well, it can't because the image is read-only. I mean, can you imagine the carnage if individual containers could modify shared images without the other containers knowing? So, instead of modifying the file inside the image, the container locates it in the layers down here, makes a copy of it in its own writable layer, and makes the change there. That way, right, the container gets the full read-write experience, but without having to have write access to the image. And we call this copy on write. Anytime the container needs to write a change to an existing file, it makes its own copy and writes the changes there. Cool. Well, switching tack a bit. From an OS perspective, we know that every container is its own isolated part of the OS, Linux, Windows, whatever, yeah? Well, that's not massively different from a VM on a hypervisor. Only, instead of virtualizing hardware resources, containers are virtualizing operating system resources, file systems, process trees, network stacks, yeah? Now, from a lifecycle perspective, we can start containers, stop them, restart them, pause them, and delete them. And until we actually delete them, they stick around. The techie term is persist. So, stopping or pausing a container does not get rid of it, nor does it get rid of any of the data inside of it. Everything sticks around till we tell it to delete. You know what? Just like a VM, yeah? Start, stop, restart. Then once we're done, boom, delete. Now back to the OS for a second. Linux containers need a Linux kernel, and Windows containers, they need a Windows kernel. So as portable as containers are, if you build your apps for Linux, they are only going to run as Linux containers on a Linux Docker host. And the same goes for Windows. If you're writing Windows apps, they're only going to be Windows containers on Windows Docker hosts. Because remember, all that's really in a container, so all that's in that isolated set of namespaces, is a bunch of files. Now, obviously, these include your application and dependencies, right? But the point is, there is no kernel inside. Every container on a host shares the host's kernel. So trying to run a Linux container, so one that needs a Linux kernel, over here on a Windows host? Yeah, good luck with that. Now, I know Windows has got a couple of ways that it can run Linux containers, but both of them make it so that Linux kernel primitives are available to the container here. So I guess, yeah, you can run Linux containers on a Windows machine, but there's magic going on to make it happen. Now, amid all of this, right, I want to make sure we don't lose our focus. Containers are all about apps. And the so-called gold standard when it comes to containerized apps is microservices. This is where each container generally runs a single process and has a single job. So instead of a monolith like this, we break each function out into its own container. And then we glue everything together with APIs, hopefully simple, documented and versioned APIs. The idea though, at the container level, is that you keep your container as small and simple as possible. In the Linux world, it's usually going to be a single process per container. And that process does a single job. I don't know, run a web service or something, yeah? This way though, we get separation of concerns and all the other goodness that comes with microservices. But containers are not just for microservices, and I've been beating my drum about this for ages. You can totally run some of your more traditional apps in containers, and all without the scary thought of having to refactor into this microservice scariness. And Docker Inc., or Big D Docker, yeah, they're well on board with this now with their modernizing traditional apps program, where the idea is something like this. Take a bit of a safer, phased approach. So lift and shift one or two of your traditional apps into a container as is, no code changes, nothing like that, but still get the benefits of containers. And then once you're done with a bit of that and you're a bit more comfortable, I don't know, maybe then you start looking at rewriting some of the stuff, microservicizing it. I just made that up. Anyway, look, that's the big picture. A container is basically a thin writable layer on top of a read-only image, and it's a runtime construct, so an execution environment for an app. Every container gets its own file system, process tree, network stack, all of that jazz. They've got a life cycle not unlike a VM. Start, stop, restart, and delete. And we can lift and shift some of our traditional apps into them, and that's fine. In fact, Docker Inc. will probably even help you do it, probably for a price. They are a business after all. But the ideal for a container is that they should be treated as ephemeral and immutable. We don't half love our funky words in the tech industry. Okay, by ephemeral, we mean that they're short-lived. You're not usually aiming for your containers to have year after year of uninterrupted uptime. Then immutable, this means we really don't want to be logging into them and poking around. The idea with containers is that we build the image and deploy the container. Then when we need to fix and change stuff, we build a new image with the fix, and then we switch out the old containers for new ones. None of this logging on and making fix after fix after fix, which, in my experience, rarely gets reflected back to the gold build. Anyway, enough theory. Let's hit the